Okay, we're live. This is Pete Giuliano's presentation on valve construction in 2021. He may mess up and call them tubes, but Pete is a master home builder. He's built a lot of crap. Crap that stands for cool, radios, and projects. He's a co-host. He's a co-host of the Solder Smoke podcast, and has a blog where he soon there'll be links at the end of the slideshow. But he posts a lot of things, works on a lot of interesting projects, and he's been drawn back into tubes. And I've seen this. This is some really good stuff that is going to apply to whatever you want to build. Some really good talking. So take it away.
Yeah, good morning. Good morning, everyone. And thank you for inviting me to the virtual convention so I could talk a little bit about glow bugs. Next slide, please. Before I start, we have to have a product disclaimer notification. And those who know me know that I'm kind of synonymous with QRP single sideband transceivers. I've built over 50 of them. And for me to talk about vacuum tubes and CW is like brown shoes with a tuxedo, but I wasn't sure this was going to be formal, so I did wear my black tie this morning. But as you look at this presentation, keep in mind what I'm really pitching is a process. And you'll see a lot of process in this, and the process is applicable whether you're working with vacuum tubes or solid state devices. Now, there's a lot of additional construction information at, I've set up a website, and you can see the URL there, and it's referenced throughout the presentation. And as a matter of fact, for those of you who are going to try to anxiously copy down information from this presentation, I've included the PDF copy of the presentation on the website, so you can download that. There's some parts lists and what have you. So don't worry about copying it down now, because the PDF is up there on that website. Next slide, please. A cautionary safety alert. We're working with high voltage DC, and you've got to really be sensible and careful about what you do. And it's the one hand rule. In other words, you don't put both hands in the hardware, one hand behind you and one hand in there. And as a matter of fact, if you like Chinese food, get a pair of wooden chopsticks and use the chopstick to poke around, because high voltage is present and it's dangerous. And you always have to assume that high voltage is present. And keep in mind, you can smoke parts just as easily with vacuum tubes as you can solid state. And our goal is an SPI of 1. Oh, an SPI, that's the smoke part index. You want to try to smoke less than 1 part on every project. So again, it's really concerning that you be careful with high voltage. Next slide. Okay, we have to bust some myths here. First of, people will say, oh, it's too hard to work with tubes. You can't find parts. Solid state is better. That's simply not true. And if it's built right, it'll work right. Next slide. Here's a view of our hobby from about 1910 to 2021. And when you look at transmitters, the topology, up until about 1960, it was almost exclusively tubes and valves. And of course, on the front end, there was even some spark gaps. But after 1960, and if you're about 61 years old, likely all you know is solid state transmitters. Very few tube projects are really coming to the forefront. So you ask, why would you build a tube or valve type QRP rig? Well, first up, tubes are still available. You get a chance to do metal bashing. I got to tell you, during this COVID-19, there's nothing better than chunk a piece of metal in the vise, take your ball peen hammer and beat the hell out of it, because it reduces stress. So you do get a chance to do some metal batching. It's more than just clicking on Amazon and ordering parts, and part of it is scavenger hunting the parts that you need. And they turn up in the strangest places, either friends or other websites, or you might even find some in secondhand stores. I found some keys, believe it or not, CW keys in a secondhand store. Circuits are relatively simple. By the way, you'll be joining a very elite group of builders. You know, not many people build with tubes, so it's kind of an elitist group. And overall, it's a mind challenge. But, you know, there are always the concerns because it's out of your comfort zone. You are working with high voltage. We have to deal with signal quality, including chirps, clicks, and burps. And I'll describe what a burp is. And you do need some support test equipment and tools like tube testers and Greenlee chassis punches. I mean, no person working with tubes and valves doesn't have a tube tester or doesn't have some sort of a chassis punch, but we're going to cover that. Next slide, please. Where to start the journey? The first thing I'm going to tell you to do is turn off the soldering iron. We're not going to be soldering right away. We're going to be doing a lot of research. And one of the best places to start is with the Sprat. And it is possible to search the index of Sprat for a lot of really great tube projects, but you have to follow the process and how to search Sprat. If you don't do that, you're not going to turn up with much. And I'm going to help you. If you look for Sprat 106, you'll find a wonderful project by SM7UCZ. That's Johnny Appel, and it's got a really nice tube transmitter in there. By the way, if you visit his QRZ page, you'll see a Wadden Mark 7 Q2 transceiver. And for those who are not familiar with that, that's a pair set. So you can see a pair set that he's built and is using. Also, the regular column by G3VTT has chock full of tube type rigs. So download the Sprat index and paw through that, and you can find some wonderful projects. So it's a good resource. Check the older ARRL handbooks prior to 1970 because they had a lot of projects, tube projects. Seems like after 1970, it turned out to be an advertising magazine for Japanese transceivers. A wonderful place to stop is N4TRB's Compendium RCA Ham Tips and GE Ham Noobs. Just do a search in N4TRB, and these were little leaflet pamphlet projects from RCA and GE. Of course, they wanted to sell you tubes. And they have some wonderful projects in there that are all valve related, and they cover the period about 1940 to just before 1970. And it's a wonderful tour through there. Also visit YouTube and search on valve and tube transmitters. Lots of projects there. One particularly good site is in the link there from VE7SL Jim McDonald, and he covers the Tritech oscillator. The Tritech ruled the roost from the 30s through the 40s and 50s, and was really quite popular because it's a combination Tritech oscillator. So part of the tube is used as a triode and part of the tube is used as a tetrode. And it was very, very popular. And Jim does an amazing job. You'll see he built a one tube transmitter that he has operating on 10 meters because this particular transmitter topology is very good for harmonic operation. As a matter of fact, the big allure with the Tritech was you could buy one single crystal on 80 meters, like 3520, and it doubles to 7040 quite nicely. So that was the idea during the 30s when the Depression hit. Guys couldn't afford multiple rocks. So buy one rock, you get two bands, and that was the allure with that. By the way, public service announcement, turn off your nano VNA. You will not need it during this presentation. Next slide, please. Here's what a little bit of research will turn up. If you look on the left, you'll see a February 1959 RCA ham tip, and that is a complete portable valve QRP 40 meter CW transceiver. Now, we've heard of machine guns and violin cases, but this is a QRP transceiver in a typewriter case, and there is a connection here. The Thompson submachine gun was also known as a Chicago typewriter. So if you look on the right, you'll see I was enthralled with this project. Matter of fact, I got that February 1959 edition when I went into a radio store in 1959. And many years later, I built a version that was solid state, but has a crystal filter in it. But that National Velvet Vernier dial just calling you to operate me. And there's a link at the bottom, and you can click on that link, and you'll hear the transceiver in operation, and it also covers how it was put together. So some inspiration from the past causes a project in the future. Next slide, please. Okay, if you fail the plan, you plan to fail. So we have a little process here. As I mentioned, this is process oriented. We're going to do the research. We're going to establish some criteria for evaluation of circuits of the past. We can look for the best practices. We see what not to do, and we formulate a plan, and we start building the building process. And in some cases, we see we don't have parts, or the parts are hard to find. And I'm going to show you how you can fabricate some parts. Document what you do, so you have a documentation trail. Later on, you're going to go back and say, how did I do that? So write down what you're doing and build in a logical sequence. You measure twice and cut once. And we have some wonderful tools that are at hand here, like the reverse beacon network and the web-based SDR receiver site. So once you get this built, you can put it on the air and actually get some reports back if anybody hearing you. And then this also gives us a chance to measure the results versus the expectations. Next slide, please. So what are we looking for in the schematics? But first, it's clear that we want to have a goal for any homebrew rig is a clean output. If you look at the output and it looks fuzzy and it looks truncated, it's not clean. So the goal of any rig, whether it's solid state or vacuum tube or valve, is you have a sine wave that comes out of that rig that looks like that. And when I look through all these old circuits, I found that many do not comply with the current regulations. As a matter of fact, anybody built a Tuna 10.2 version 1970 will find that ARRL had to reissue that in the 90s and 2000 to put a different low-pass filter on it so it complied with the current regulations. Many of the circuits cut corners and they leave out features, and they don't address the critical safety considerations. You're going to see that here in a second. Anyway, I came up with a criteria list. And this criteria list, whether you're working with tubes or solid state, is a good list. I mean, you want to look at the power supply filtering. You want to look at how hard is it to build, the type of oscillator. Should I have multiple bands or a single band? Standard parts, standard configuration. So these are the criteria. When I looked at these schematics of the past, this is what I used to say, is this good? Should this be kept? Is this appropriate? Should I not consider something? And you'll see that in the following circuits. Next slide, please. Now, this is straight out of the ARRL handbook, and these are the forms of oscillators. And essentially, we're going to be building an oscillator. And at the top is the Tritech, in the middle is the modified Pierce, and on the bottom is the grid plate. Now, I'm going to call out some things, and I want you to just keep in mind what C2 is, C2 in each one of these circuits. And we're going to discuss something about C2. But you need to be careful when you look at these schematics from the past, because they can fool you. If you look at the Tritech, when I first looked at it, it looked like L1C1 and L2C2 is like an IF transformer, or these I've seen in the past where they put two tuned circuits like that close by so they get some feedback. Well, it's not. It's just the way it's drawn. If you look at the top of the L1C1, you'll see it's grounded. Typically, you see L1C1 180 degrees and it goes to ground. It's just the way it was drawn here to fit on the page. It can fool you sometimes. So you need to look at these circuits carefully. Now, interestingly enough, these three circuits, you have to be concerned when you tune the tank to resonance, it may stop oscillating. But there's some tubes like the 6AG7, 6AH6, 6CL6, 5763. They somehow work because of the physical constriction of the tubes. They won't necessarily do that. And if you look to the left here, they talk about the loaded versus unloaded condition at resonance. So it tends to be broader with those specific tube types, so that you have less of a situation where you bring it into resonance and suddenly stops oscillating. But I have a view. Pick a form that reduces the chirps, burps, and key clicks. And also, you have to look at something that can be done safely and has safety built in. So it's really important. Again, look at C2 in each one of these diagrams. We're going to talk about that a little bit more. Next slide, please. Okay, what makes an oscillator? What is an easy way to envision an oscillator? And I know there are people listening to this presentation or looking at the presentation say, I want to know everything about oscillators. I want to see the schematics. I want to see the physics. I just won't take it that it oscillates, but I need to see that information. Click on the link below. That tells you all about the basics of oscillators. And here's a non-scientific offering about an oscillator. It's like an amplifier with feedback. You know, you take the old audio amplifier, you bring the speaker near the microphone, and next thing you get this terrible howl coming out of the speaker. Well, that's an external situation where you bring the microphone to the speaker, but internally in an RF circuit, the feedback is built in. And if you have the feedback as such that K beta, which is the feedback ratio, is greater or equal to 1, it will oscillate. This is known as the Barkhausen criteria. And I remember when I was in engineering school, the professor said to me, Pete, 50 years from now, you're not going to remember all that crap. Just remember, if it doesn't oscillate and it's all wired up right, K beta does not equal 1. So K beta has to equal 1 or greater than 1 for it to oscillate. And you can find that in the link. Now, we're going to build a crystal oscillator. And well, we need to go back. I just finished that up before we go into that. The crystal oscillator, the FT243 are not plated oscillators as such. And there was a little wafer in there, a crystal wafer that's about the size of slightly smaller than the postage stamp and about the thickness of 2 stamps. And that's what it's put in an electric field and will oscillate based on the specific dimensions of that crystal and quartz crystal. So many enterprising hams would take the FT243s apart. They'd get an HB lead pencil and they'd go back and forth over the top of the crystal, and they would actually lower the frequency because you added to the physical dimensions. Or if they wanted to raise the frequency, they get a piece of plate glass, they get some household cleanser, the real abrasive kind, they pour it on there, put some water in there, make a paste out of it, and you get to do the ohm trick. 300 times you go in a circle, and each time you go in a circle, you say ohm, ohm. And typically what happens is you'll peel enough off there to raise the frequency. But most times when you either put the lead on or you kind of etch the crystal using the abrasive compound, you put it back together, it didn't work. But some guys were really careful and really clever in being able to do that. Now, question is the crystal controls. Are limiting? Short answer, yes. But there's some QRP watering holes like at 7030 and 14060 and 21060 and I don't know all the other I think 10.136, something like that. There's people clustering here. So even though you have one crystal, you can make a lot of contacts, but it is limiting. If you want a QSY, it's kind of hard. You're going to need a whole box full of crystals, but picking those frequencies works quite well. Next slide. We're now going to cover a series of what I call the good, bad, and ugly. And what I've done is looked at a bunch of schematic diagrams from the past, and I've tried to highlight some things, and I do it with a red circle. And I also try to make an evaluation of that circuit based on the criteria that we saw before in an earlier slide. And this is from the 1957 ARRL handbook. And I kind of class this as bad, and here's the reasons why. First, there's not a 3-wire plug coming into that thing, and there's no fuse. So the tube is the fuse. Or if you have a short in there, you could actually smoke that transformer. I don't know why it doesn't have a fuse, and I'm not even sure back then they had a polarized plug, but that's not safe. That is not safe without a fuse in there. The other thing is the electrolytic capacitors in the filter are 8 microfarads at 500 volts. Those are a little skinny in terms of what their value is. And if you look at the approximation of what that value should be, it's the current drawn in the numerator, and the denominator is 2 times the frequency. So it's either 50 or 60 hertz. So that could be either 100, 120 times the volts peak to peak ripple. And if you work that backwards with a current of 50 milliamps to feed that circuit, you'll find the peak to peak ripple is about 55 volts at 8 microfarads. So I have 55 volts of ripple riding on 350 volts. That's about 15%. You don't think that signal is going to sound like a buzzsaw? So just by inspection, if you make that VPP small, you're going to have a larger capacitor. If you reduce that to 4 volts peak to peak, that C8 gets to be about 104 microfarads. So having more capacitance in that filter is probably better. I don't know, it might have been a cost factor. I'm not sure. but certainly in some of the other circuits you see it's a significantly bigger value. And one of the things is you'd say, well, 100 is good. Let's put a 220 in there. And the problem is when you power that thing up, it looks like a dead short. So oftentimes they'll use a step start circuit, but I won't go into that. But like on high voltage supplies, they use a step start. So you only put half the voltage on the primary until the capacitor charges, and then you hit it with a full voltage. And I happen to have a 3000 volt 1 amp supply that's got a microcontroller that does a step start. And right above the filter capacitor is a 100 milliamp meter, 50 or 100 is in a plate circuit. Now, you're very careful when you build everything in a chassis so that nothing is exposed except you put the plate meter right on the front panel, right square in the middle, and there it is, 350 volts right on the terminals of that meter. Gonna nail you. So unless you put some protection around that meter, I'm kind of against putting plate meters in there because there's other ways to measure the current. You could put it in the cathode and that would certainly do it. Another factor here is in this circuit, the screen grid is acting as the plate. So what you have there is a 22K 1 watt resistor that every time you key it, you're getting a voltage drop across that resistor. There's no regulated voltage on that screen. So you're going to get a whoop whoop sound very definitely. And the other thing is the output tank circuit in the Pi network, it says C text. You know how they change bands? They got an alligator clip and they move the alligator clip along the coil. So yeah, that worked out kind of good, but you got to be careful you're not keying while you're changing the alligator clip because you're going to get burnt with RF. So that's not a really good idea. Plug-in coils are far better. And also in the cathode circuit, they have a couple capacitors in there, and that's to act as a key click filter. Now in the web link, I have a link in there about block grid keying, and it also covers key click filters. So you can click on that link. That's a way that to handle that so you don't get key clicks, and it's block grid, or you put the resistor and the capacitor combination so that you soft key it so you don't get that click. So anyway, I class this as bad primarily because of the safety features and primarily because of the undersize of the filter capacitors. Next slide. Okay, here's the Tritech. The Tritech was discovered in 1933, and here's a 1936 article. And it's classed as a very stable oscillator. That's the triode section. And the tetrode section is actually a harmonic generator. So you got a lot of harmonics coming out of that. And what do I have? I have link coupling to an Ed-Fed wire. So where do you think those harmonics are going? Right out to the antenna. So you don't want to build this and put this on the air today. Now, it's really kind of interesting because the L1C2 combination, and I heartily recommend it. You look at VE7SL, who gives a much better explanation than I ever could. Actually, for the triode, that's the tank circuit. That's the tank circuit in the cathode is the tank circuit for the triode oscillator. If you look at pin 4, it's connected to C3 to ground. That means for at RF, that screen grid is grounded for RF. So the tank circuit is L1C2. Now you got to worry a little bit because this was called the crystal buster. And Steve also describes why guys held the key down too long and you got a lot of grid current going through that crystal. And as a result, you burn it. And there's also another issue, and Steve told me this in an email. Watch L1 and C2 is not resonant in the crystal frequency. You want to make it something different, and you'll see that in a subsequent design. It has no key click filter as well. So I call this kind of ugly because of the harmonics going out in the Ed-Fed wire. Next slide. Okay, here's AA7JC, and he gets sort of good. He's got a fuse, and he's got a neon lamp on the primary so you can see when the power is applied, but it'd be nice if you put a 3-wire plug instead of a 2-wire. He does have some 40 microfarad electrolytics, better than the 8. He's got a nice bleeder on that. He's got a voltage regulator circuit, so he's putting a regulated voltage on the 60Q6. It would have been nice if he put a key click filter, a resistor in there, and then move the tap up between the resistor and that capacitor, insert it right between the inductor the 2.5 millihenry choke and the capacitor forming a key click filter. Now, he does have metering on this, but he's sampling the RF on the output. So he's TFMSing, tuned for maximum smoke, TFMS, tuned for maximum smoke. Now, AA7JC says he gets 12 watts out at 70 volts peak to peak. Now, I don't know if you can see the graphic, but the graphic is obscured on my screen by the participants. But the little graphic shows volts peak to peak, volts peak, and volts RMS. And the volts peak is half of volts peak to peak. You just divide it in two. And volts RMS, which is used in power calculations, is 0.707 times the volts peak, not the peak to peak. So I'm going to give you a tribal knowledge tip here. First of, AA7JC says 70 volts peak to peak is 12 watts. Actually, it's 12.25 watts. And the reason I'm going to call that out, some of you listen to this run no more than 250 milliwatts and are working DXCC. So, I mean, that's QRP level, and he ignores it. But how can you convert 70 volts peak to peak into watts? And I'm giving you a tribal knowledge tip. Take the 70 volts peak to peak, square it. You get 4,900. Take it times 2.5, and you get 12,250 milliwatts. And you say, why are you working in milliwatts? Because with my calculator, if I take the log of that number and take it times 10, I get dBm. So it turns out 12.25 watts is 12,250 milliwatts and is 40.88 dBm. Run a test here. You got a 1 watt rig, 1,000 milliwatts. Log of 1,000 is 3. Take it times 10, that's 30 dBm. If you have 44.72 volts peak to peak, you do that math, and guess what? It comes out to 5,000 milliwatts, and that's 37 dBm. So you have to see 44.72 volts peak to peak to have a 5 watt output. But the tribal knowledge tip, take the peak to peak, square it, take it times 2.5. That 2.5 factor already has built into it a factor of 1,000, 50 ohms, what have you. That only works for 50 ohms. Now, there's some in here that only work in RMS. I don't give me that. I only deal in RMS. Okay, so to get RMS, I have to take the volts peak to peak divided by 2, and that's 35, and then take it times 0.707. So instead of dividing the volts peak to peak into the by 2, divide the 707 by 2, and you get the 35-35 rule. So if you take 35 times the volts peak to peak, you'll get RMS. You square that divided by 50, but wait a minute. I still have to multiply that by 1,000 to get dBm. So it is a practical factor, though, because recently I was involved with a project. A group was building my simple single sideband transceiver. And a guy says, oh, I measured 100 volts peak to peak. He said, that's 50 volts RMS. And I said, no, if you just use the rule of thumb, one third of the volts peak to peak will give you RMS. It's not exact, but it'll give you a rough estimate if you're doing calculations. So tribal knowledge tip, volts peak to peak squared times 2.5, take it times the log, take it times 10, and boom, you got dBm. So a couple tribal knowledge tips, and that works with solid state or vacuum tubes. Next slide, please. Okay. This I classified as bad, and here's the reason why. Again, the power supply, probably not a polarized plug, no fuse. By the way, he's showing 450 volt. That transformer, he's producing 450 volts DC, and he's got a 68 microfarad, 450 volt electrolytic in that. First, that electrolytic is undersized because I guarantee you're going to get more than 450 volts out of that, and you're right at the margin. There's another problem with that, is there's no bleeder. There's no bleeder resistor. And I said, always assume high voltage is present. You could turn that rig off, come back an hour later, and I bet you see 450 volts in that 68 microfarad electrolytic. Now, there's somebody in the back room jumping up and down saying, oh, wait a minute, there's a way to solve that. Yeah, there is. When you open the switch, hold the key down because that'll drain that electrolytic. But lots of people don't remember that. So it's better to have a bleeder resistor on there. Now, in the website that tubes and valves, I show a little tool called the chicken stick. And the chicken stick is a broom handle with a chunk of wire, and it's got a pointy end on it, and you put the wire to ground and you hit that 68 microfarad and it discharges it. But don't do it with a screwdriver. Use the chicken stick, and I have the dimensions and the design of how you do that. So this is a real problem because of that, the power supply, and because of the danger it poses without a bleed resistor on there. Now, good news, they got a voltage regulator on pin 4. So you're going to regulate that voltage. That's an OD3 VR150. They got a Pi network, but you really need to pay attention to the safety issues that are involved with building these transmitters. Okay, next slide. Okay, here's another one from ARRL 1961 handbook, and I kind of class this as sort of bad. Again, the same power supply that you saw in the very first one. No fuse, probably not a polarized plug. The electrolytic capacitor, you're probably going to get a buzzsaw noise in that. There's no click filter, although they do have a regulated voltage. And it's kind of interesting that they use an NE2 glow lamp and a relaxation oscillator to produce side tone. This is one of the few with a side tone in it. And that's something that I don't know, I can't send without a side tone, and some people can, but a good friend of mine has the DX100, and what he uses for a side tone, when he keys on CW, the transformer hums. So he listens to the transformer humming, and that's what he uses for side tone. But anyway, I'm going to ask another question. Remember C2, C4, R1, and why is that RF choke on the output? And we're going to describe that. And again, I would use plug-in coils, not a tap, because now if you have a tap coil to change bands, you're going to have to put that tank circuit near the front panel. You're going to have a band switch. It's got to be rated properly. Just make it, if you want to do something, just make it plug in. Next slide. Okay, first noteworthy here, look at the output coupling capacitor off the plate. And that's it's 10 nanofarads, 600 volts. That's undersized. He's putting 350 volts in that. That's undersized. So not a good value. You ought to put at least a 1.6K in there, or at least 1K voltage rated. Matter of fact, one you're going to see a little bit later doesn't put anywhere the plate voltage. They got a 3 kV in there. So these things are spot. Again, no regulated voltage on pin 4, which is going to cause a little chirp on the signal. But what's more importantly is take a look at that 2.5 millihenry choke across the crystal. And one test the old timers used to do is they'd pull out the crystal and they'd key it. They'd pull out the crystal and they'd key the rig. And if you got an output, that meant you had a parasitic oscillation somewhere, or something in there was resonating an LC circuit. So if I pull out that crystal, I have a 2.5 millihenry choke from the grid to ground, and I've got interelectrode capacitance, and I got straight capacitance. And if you did the math of saying a 2.5 millihenry choke with the straight capacitance, I got a 2 network that resonates at 1 megahertz. So you have to look at that, and that's why R1 in the Tritech was to prevent it oscillating. So you need to lift that 2.5 millihenry choke and probably put a 100K resistor in there. That's why I said, remember R1, but this is something to spot in here. So the fact that it could, in fact, put out a signal without the crystal in there, and also the plate coupling capacitor looks a little small. Okay, next slide, please. All right, I didn't miss a block here. It's not sort of good or it's not sort of bad, but there's some important things to look at. First of high marks, 3-wire plug. There we go, 3-wire, and it's got a fuse. Hey, how about that? And if you looked at the electrolytic capacitors, they're at least a reasonable side. You're probably going to get maybe 25 volts of ripple. But indeed a good job. He's got a nice bleeder resistor on there. And for the moment, just ignore the circle around the switch, and let's assume the switch is closed. When the switch is closed, what happens is the 6AG7 part of the circuit is powered on. So you're not keying the oscillator. The oscillator is turned on, and essentially is what you're keying is the amplifier, the 6L6. And look, he's got a key click filter near the 200 ohm with a 0.01. So he's doing a little keying shaping there. But one problem with having the oscillator on all the time and then keying the final amplifier is a phenomenon called backwave. Some of that oscillator energy can sneak through, even though the key is up. So you might be able to hear that signal, even though the final is not being keyed, and that's called backwave. So let's look at, this is a modified Pierce, and there's no regulated voltage on the screen grid. So if I were building this, I'd just, at the junction of the 2.5 millihenry, the 10K 5-watt resistor and the 0.01, I'd take 150 volt 5-watt Zener and just slap it in there, and I'd have a regulated voltage. But more importantly, you're having maybe 150 to 200 volts on that screen grid. And look at that 0.01 or 1,000 picofarad that goes from the screen grid to the crystal. What voltage rating do you put? Now, if you're solid state guy, say, yeah, I got a 0.001, just grab one, a 50 volt, put it in there. And guess what? You're going to short that because it's too high a voltage for voltage rating of that capacitor, and you're liable to smoke that crystal. So it's important when you're looking at these to make sure you understand what voltage levels exist, because you want to put the right value in there that's appropriate for the circuits being used. Some of those, cutesy capacitors that you can buy that are 50 or 100 volts aren't going to work in this circuit. Okay, moving next to the tank circuit with a 100 microfarad and L1. Now, unless the capacitor there, the 100 microfarad, is a trimmer across the tank coil L1, you cannot use a standard variable capacitor, the kind that has a grounded rotor, in that application, because you got high voltage on that. You got high voltage coming in on that. So you're going to either have to, if you got a metal chassis, you're going to have to insulate that capacitor off the chassis, or you're going to have to put an insulated coupling shaft if you're going to run it out the front panel. Having a trimmer in there makes it inconvenient, because every time you put a different crystal in there, you try to QSY, you're going to try to want to put the appropriate grid drive into the 6L6. So with one little simple modification, you could use a capacitor, and we're going to talk about that here in the next slide. But it's important to note, if you hooked it up like this, you cannot ground that capacitor because you got high voltage running through it. So you're going to have to insulate it from the chassis, insulate it from the front panel. And that's kind of a bear to find that kind of stuff today. I mean, in the past, that was easy to do. Today, it's kind of hard because you can't find those parts. Okay, let's move down to the switch. Essentially, the switch is in the high voltage circuit, and it supplies voltage to the oscillator. So the oscillator runs all the time, and then it supplies voltage so that you can key the 6L6. And just think about it. You have this cutesy toggle switch that's good for 250 volts AC, probably at 1 amp. But we're not running AC through there. As a matter of fact, one time in my life, I used to sell micro switch, and a customer would say, I need a micro switch. And I said, what are you going to use it for? He said, hey, I'm going to use it for the switch. I said, no, tell me what you're going to use it for. Many of the micro switches were rated for 250 volts AC, like maybe 1 or 2 amps. But the DC rating was only 30 volts DC. You're running 350 volts through that dollar switch you got that looks really cute on the front panel, but you at risk of blowing that switch or worse, getting shocked. So it'd be better to move that switch into the center tap return that's grounded on the transformer. And you'll see some of the circuits of the past, they put the switch there. So opening the switch opens the ground return, closing the switch essentially completes the circuit. So you got the high voltage. So that's a real problem. You could put a relay in there and control it with a separate switch, but the relay has to be rated the same way as the switch contacts. That's not a really good idea with a switch without designating what it has to be and what kind of voltages are on it. So just keep an eye to that. Again, the panel meter with the high voltage on it, and that could be a risk to you personally because of the fact that it's probably everything underneath the chassis is all protected by the chassis itself, but you got that panel meter with some high voltage on it. These are things that you need to look at when you're reviewing these circuits. And it's not unlike what you do with solid state. Solid state, you have to worry about ins and outs. I mean, you got to keep the ins separated from the outs. So it's the same kind of process as you're looking at schematics and actually the physical construction and what you need to do. Okay, next slide. All right. No, back one. There you go. Anybody familiar with WA5BDU? That's Nick Kennedy. If you built any crystal filters, that's the man. He's got some wonderful papers on how to build crystal filters. In this case, it's a 2-tube rig. And if we look at the topology, I said this is sort of a good design, and I'll go over some points here. First off, it's the Tritech. And it's drawn here so you can see that the Tritech is grounded. And if you do the math with L1 and C1, you'll see that resonant frequency is about 9.2 megahertz. So he's operating on 3 bands. He's operating on 80, 40, and 30 meters, 80, 40, and 30. And the 9.2 is not in any of those bands. So the likelihood of being a crystal buster, I think he's taken care of there very nicely. Okay, to answer the question, I keep saying about C2, C4, and in the last schematic, I said you had to isolate the capacitor. If you look at C2 and C4 across L2, they're in series. C2 and L4 is in series, and they're using the common ground as a connection. So it's like the 1 ohm resistor and 100 ohm resistor in parallel. Capacitors in series are just like resistors in parallel. So essentially across the L2, you got the 150 picofarad capacitor because you got 150 and 10 nanofarads. In the prior circuit, if the guy had just clipped that lead and grounded the rotor, you'd do the same thing that Nick has done here. So across that tank, L2, you essentially have C2. So that's why I bring that up, is you need to look at that, because clipping that lead sure makes it easy. You don't have to do all the physical isolation and worry about DC voltage on the rotor. Now look at R4 on the 5763. R4 has a 7.5K at 1 watt, 7.5K at 1 watt. Okay, if we move over to the 6CL6, what Nick has done is he's got 250 volts being supplied to that circuit, and he's running that through a 10K resistor, and he's got 4 Zener diodes. They're 36 volts a piece, and if you add those up, the total drop across the Zeners is 144 volts. So he's dropping from 250 down to 144. The difference through that 10K resistor is 106 volts DC. So 106 volts DC through a 10K resistor, and you do the I squared R, you got 1.1236 watts being dissipated through that resistor. Now, typically in these circuits, any resistor like vacuum tube, any resistor that's not named, usually they say all the resistors are 1/2 watt. So if you put a 1/2 watt resistor in there because it didn't designate it was a 1 watt or a 2 watt resistor, you probably smoked that resistor. I think Nick knew it had to be a 2 watt resistor. It's just, it didn't get picked up on the schematics. So these are things you need to look at when you're looking at schematics. What am I dropping? I'm dropping 106 volts at 10 milliamps, comes out to over 1 watt. So I need to have the appropriate size and wattage rating. Now, something else interesting, if you move over to the 5763, he probably couldn't find a 2.5 millihenry choke. So what'd he do? He took 2 1 millihenries and series them. There's nothing wrong with that. But, you know, the thing is you do what you got to do, but that's kind of clever. Now, he has a note there that C10 was added, and that C10 is in the cathode and the suppressor grid. So he was keying that's what he's keying on the cathode to ground. So he added that capacitor. I would have liked to seen a resistor in series with that capacitor to those. So we had a little soft keying there. But the other thing I think is important is he's tuned for maximum smoke. He's made a little transformer there in the output. So he has a 1 turn and 22 turns, and then he's feeding that into a diode, and he's got a essentially he's looking at the RF output. It's a DC voltage, and he's got a way of calibrating the meter. So that's really good from that standpoint. So this is a good design. It's Tritech. He's got the regulated voltage. He's letting the oscillator run all the time. He's keying only the final. He's tuning for max smoke, so he's not putting a high voltage through a meter. So it's really good. And these are things, when you look at these designs, and whether this is a tube or a solid state, this is the thing that you need to be aware of, is all these little points, so that you're looking at the circuits in detail and you're understanding what parts should be. Now, look at his plate coupling capacitor. It's 3 kilovolts. And the other one was 600. That's 3 kilovolts for a reason. So these are just things that you pick up. Okay, next slide. Okay, where does this lead us? First, pretty clear, you need an intrinsically safe power supply. Got to have some fuses in it, 3-wire. You got to have the right kind of filter capacitors. The form I would pick, I would not go with the Pierce. I would go with the grid plate or Tritech. And by the way, a good friend of mine has a shrine to Gene Shepard, who was a famous radio host and famous ham. And I want to shout out to him, let him know that Gene Shepard loved the Tritech, as this was his first rig. So you had to need to add one piece of information to your shrine bill, so that you now know that Gene Shepard was a fan of the Tritech. Regulated screen voltage on the oscillator. By the way, there's an excellent paper by G3OTK, an excellent solution. He's got some op amps in there to actually form the keying, and there's a link there that shows you how to do that. Metering of the RF output, we do it in the cathode circuit, or we do it in RF sense. I would avoid the plate circuit. Too much of a possibility of having high voltage exposed through the meter terminals. You want a pi network output, and I even added a low pass filter. And you want to do some shielding between sections and high voltage screening. I mean, make it in such a way that you make it impossible to stick your hands in the high voltage. You want multi-band operation, forget those band switches and that, make it plug-in coils. This is important for me. I suffer from FFS, fat finger syndrome. My fingers are fat, so allow yourself some room so that you can do some things. And the other thing is, use high quality components and voltage rated parts. Next slide. Okay, the chosen approach, we're going to do a 1-tube valve configuration with a pi network low pass filter. Now, despite the list of preferred tubes, I happen to have 6V6, 6F6, and 6L6. And as the Reverend Dobbs would say, socketry. The same socketry works for either the 6V6, 6F6, or 6L6. And I picked 40 meters because I happen to have a rock. By the way, Club Sales has wire lead crystals at 7028 and 7030. And you can you can find a FT40 243 crystal case that maybe the crystal's bad or gone. Just pull that innards out of there and then solder your crystal in there, put the case cover back on, you just plug it right in there. So it works real well. So crystal availability, Club Sales, contact Graham and he'll fix you right up. I identified the rate of parts, and one thing, most of the parts were easily found except for the 2.5 millihenry chokes. We're going to make these, and I'm going to show you how to do it. I purposely avoided metal bashing because you're going to need green meat chassis punch. You're going to need an electric drill. So if you use a little wooden chassis, and I'll show you how that's done, you can build the rig on a wooden chassis like it was done. And that was a QST article, by the way. We're looking at a power supply of 250 volts minimum, 100 milliamp, 6 volts, 6.3 volts AC at 2 amps. And on the link that shown earlier, we have that very circuit diagram and shows you how to build that. We have capacitors have a voltage rating of 1 kV, except 2 that should be 1.6 kV, like we saw Nick put 3 kV in there. Resistors are mostly 1.5 watt at 5%, but there are some power resistors required. I used a pill bottle to wind the pi network, or if you have the luxury of some air ducts coil stock, you can figure out the right number of turns and use that. And I made the pi network in such a way that it has a fixed value for the load control. So I eliminated having to have a second capacitor for load control. I only need a plate tuning capacitor. And I built the W3NQN low pass filters hung on the output. So that's the chosen approach. And next slide, please. Basically, we're going to use the 6V6 or 6F6, 6L6. By the way, with the same circuit, you'll get about twice the output with a 6L6. It's just the tube has got more oomph to it. So you can, if you've got a 6V6, plug it in there, or 6F6, they're reasonable. I bought a 6F6 not too long ago, and I think it was $4 or $5 on eBay, and it was a good tube, so it works well. I have some multi-tube valve designs are presented on the web link. And I think the idea of the 6V6, 6F6, 6L6 gives you a flexibility of choice. And also, I was concerned about the complexity of the build. And the painful details are, of course, at that website. Now, I want to talk about chirps, burps, and clicks. Crystal heating. As the current passing through the crystal is a major factor of chirps. And how you mitigate that is don't run everything to the wall. I use a little feedback capacitor. It's a little trimmer, and you saw that, you might have caught that in some of the earlier designs. This little trimmer sets the K beta, and it also helps you pick the best signal. So it may not be the most power out, but it'll have the cleanest signal. And remember, our graphic, we want the cleanest signal. Now, clicks arise from the making and breaking of the circuit sort of abruptly, and you'll get the key clicks. And if you do a bit of sneaking up on the making and breaking, in other words, the keying shaping, the clicks will be reduced. Now, you heard me use the term burps. Well, for my good friends in the UK, burps arise by eating bangers and black pudding washed down with Boddington ale for lunch, and especially the bangers and black pudding had overly seasoned with garlic. Doesn't sound very good to me, but it sure will cause a lot of burps, and we don't want that. Next slide, please. Okay, here we go. That's it. There we go. We have the FT243 crystal, the 6V6. We got our tank coil. You can hardly see it there, but there's a little toroid. It's called the high voltage glitch, and a thing called the snoop loop. And what that is a one turn with a 6.3 volt. I think it's a type 43 pilot lamp. And I just put it around there so you can sense the RF and just make sure. As a matter of fact, when that glows the brightest, you got maximum RF. We've got the fixed load capacitor on the front end of the W3NQN low pass filter. I have a tuning cap, and this is what I call brown shoes with a tuxedo. So we have all these things, and it is a grid plate oscillator form. Next slide. Okay, here's the schematic for it. And I should mention that this good friend, Tech Swan, so kindly put this together for me. And there are a couple of things to annotate here. A 15K 1 watt resistor is okay if you're running 250 volts. You need to up that to 2 watts if you put 300 volts on that. And the two capacitors, the 0.001, 1 kV on the plate and on the screen, those are where 1.6 kV. I missed that when Tex drew this for me, but I mentioned in the parts list the two 1.6 kV. Those are the ones where you want to put those. And there's an X marks the spot. And that X is where we install a 2.5 millihenry glitch choke. And we first highlighted that one of the ARRL transmitter circuits, and you're going to see the Y in a minute. And then you see the values to build the W3NQN low pass filter and out to the antenna. So this is the basic schematic. You see the same information with the parts list, and the parts list is coming up here. Next slide. But first, proof of life. I had mentioned using the reverse beacon network or some of the web SDRs. So there's that transmitter here on the 23rd of August being picked up 40 meters by 2 stations. The WA7 station is in Utah. So he was picking me up in the middle of the day. And that's about a good 700-mile range from where I'm located here in Southern California. So the transmitter does get work. It was heard by the reverse beacon network. Next, please. Next slide. Okay, click on that again because there's a little video. I'm not hearing the sound. Well, that's one of those technical things. Anyway, it's probably good you're done here. You hear the sound because it's like I'm sending with my left foot. I was trying to hold the camera and I was trying to hold the key down. The key was just floating on the desk. But anyway, I have my SDR transceiver tuned up, and this is going to go into transmit here in a couple of seconds. Probably you just need to move that along, but too bad you can't hear it because you can hear me send with my left foot. Anyway, with the Snoop loop, I was able to, able to make sure I got output. And then I was also able to look at it on the SDR screen. So regrettably that technology is not working here for this. So it's unfortunate you can't see that. But anyway, using a tool like the SDR lets me look at the signal and lets me hear what it sounds like. And the nice part about the SDR that I have has a record function. So I could record it and listen to it, and I get a good feel. And I just had like 2 inches of antenna on the SDR, so it was just picking up RF in the shack, and it let me tune that little feedback capacitor so I got the best sound with the consistent output. Okay, next slide. Oh, I think I'm hearing a little bit CW in the background, but I'm not hearing much on this end. There you go. I hear a little bit. Yeah, there you go. Snoop loop. And then you'll see there's the spectrum. So use the tools at hand. I mean, the message here is having a receiver to listen to this is really important because then you get a feel of what it sounds. I mean, run it into a dummy load. Don't put it on the air. Run it into a dummy load. So this way you can hear it. So next slide. Okay, here's some pictures of the rig itself. And it's built on a wooden chassis, and the parts list that you're going to see has the pieces, the size of the pieces of wood, and they're put together with wood screws. And the where you see the N6QW in the middle slide, right below that is that trimmer capacitor that you adjust for the best sounding signal, not necessarily the maximum power out. And you can see the construction is pretty simple. You see the W3NQN filter. And in the lower left, you see some metal shields. As a matter of fact, I'm going to hold this up here so you can see. Here's the actual with the front and back metal shields. So this way I can't put my hands in there. And those are made with some tin plate that you can buy at Home Depot. And I just bent it over so that it would form a hem and make it stiff, and it works pretty well. So that's the detail, and these same photos appear on the website. Next slide. Okay, the 2.5 millihenry choke. And we said, look at this, and why is it here? And there's an important reason to have that 2.5 millihenry choke on the output. And the answer is safety. If the plate blocking capacitor, especially that guy that had the 600 volt capacitor in there, shorts, you have high voltage floating around on the antenna or your antenna tuner. So that's a concern. And with the 2.5 millihenry, the DC resistance is small. And so if you do have that shorting, it'll smoke the 2.5 millihenry where you see a huge puff of smoke coming out of the out of your rig, or it'll blow the fuse. But from an AC standpoint, if you did the impedance measurement, it's 110 k ohms. So the 2.5 millihenry are hard to come by, and you can make them. If you take an FT 5043 core where the AL is 440, if you wind that with 75 turns the number 30 enameled, you will get a 2.5 millihenry choke. Or if you got fat fingers like me, you use the FT 8243 that has a slightly higher AL number. You need 73 turns. And I happen to have an LCR meter, and you'll see that that's registering 2.5 plus. So it does work, and it is my glitch protection. I have that right on the output. So this way, in case something shorts, I'll have the DC going to ground, and with number 26 wire, it'll carry a little bit of amperage. Next slide. There's the parts list. And I try to include everything in there, including the size of the wood and what type of materials they are. And you can build that little wooden chassis, and it saves a lot of money, and put some shields on the front and back of it. And this is on the website. Next slide. Okay. Test gear likely not found in most shacks. I have a VOM good to 1,000 volts. Now, let me tell you why I used the VOM. My very expensive DVM, if I screw that thing up, I'm going to be heartbroken. But the $25 VOM, if I smoke that, I will be heartbroken, but not as heartbroken as $175. So it's a good idea that, you know, it'll tell you what you need to know, but if you smoke it, it's not a big problem. Now, I happen to have an LCR meter from AADE, Almost All Digital Electronics. They no longer make it, but it's one of the best you can buy. But you can find LCR meters on eBay or on Amazon. The Snoop loop is a one-turn loop with a light bulb. I use a non-metallic screwdriver to adjust that trimmer. I happen to have a grid dip oscillator to when I peak the tank, I can tell where the peaking is on the Pi network. Okay. This is a chance to turn on your nano VNA, and you can measure. Just make sure you terminate it when you do the measurements, so this way you get it proper. It's nice to have a tube tester, and don't overlook your SWR power meter as a handy tool in the shack. I'm surprised that some guys don't have an SWR power meter in line, but this lets you look at the output. Heat shrink heat gun is really important because you're going to have a lot of exposed wiring. Put the heat shrink all over the place, so this way you don't risk exposure. And for a TR switch, you can find a double pole, double throw nice switch. You know, it's a live type of thing to do the transmit and receive. Next slide. Now, we talked about test gear, and here is a sample of a tube tester that you can build. This one valve tester was built by my good friend Peter O'Connell, VK2 EMU, and it's based on the design from Drew Diamond. And if you go to Club Sales, they have the Drew Diamond books for sale, including volume 4, tell you how to build a tube tester. Now, Peter just completed another version of this. This happens to be customized for 6V6 or 807. He's got another one he just built that you can test either 12AT7s or 6BM8s. Yeah. I mean, it makes it kind of custom, but if you're gonna work with valves, you need some kind of a valve tester. And if you're going to buy one, look for a Sencor Mighty Mite. You can get the manual on the internet and from the Bama manuals. And I happen to have one of those. I paid about $30 for it. And boy, it's worth its weight in gold. Now, there's really something fascinating about this tube tester. Diamond designed it. And by the way, someone asked about, is he still around? And evidently he renewed his license just this year. So he's still around. He put 0 volts on the plate, 0 volts on the plate. Because as you notice that 807, you got to put that you got to put voltage on the plate cap. It's 0 volts and the cathode is minus 300. Just as long as the cathode is negative with regard to the plate, you're in good shape. Now, did we move you out of the comfort zone? But when you look at that, but just think about it for a second. Okay, next slide. See, you hit it again if you can hear the sound. Well, evidently the sound's not coming through. Anyway, thank you for riding along with me. We have a few minutes for questions. I can be reached at craponthebench@gmail.com, and CRAP is an acronym, as Brent mentioned, for Cool Radios and Projects. This project is covered with the tubes and valves, HTML. If you're into SDR, you can click on the Radio Genius. There's a story about that. I'm not a radio genius, but GoDaddy offered me that URL for 99 cents, and I couldn't resist. Many hams have ancillary hobbies, photography. Some guys play music. Some guys like to cook. I'm one of those cook guys, and there's a pizza. That's another kind of homebrew, and that Pasta Pete has quite a few recipes on it. My main site at N6QW.com, and of course, some really old stuff as at JES Systems. The power supply is detailed on the URL link that's there. And just keep in mind, if it's built right, it will work right. So I'm done.
Brilliant. Thank you very much, Pete. And we've just got to wait, I think, for Brent to come back, who was chairing this session. He had a slight problem. So if you just pause for a second. And first of all, my apologies, Pete, because I hadn't spotted there was audio, and we had these problems with these awful blocks that we managed to get rid of on the screen while you were talking, thanks to David, who sent me a message about a solution to it, which was absolutely fine. So we did our very best, and but someone said this is the problem when you get a bunch of amateurs together, which is probably true.
well, it's a good thing you didn't hear me send with my left foot.
I heard it, but of course no one else did, sadly. But it sounded good to me. It sounded fun. So we're still waiting for Brent. While we're waiting for Brent, I'm just going to dive quickly into Q&A. So Mike was asking what valve test did you use yourself? He said we have Avo and Mullard here in the UK.
I'm sorry, I didn't hear that question.
Mike was asking what valve test did you use yourself?
Oh, the Cencor Mighty Mite. Cencor Mighty Mite, and this can be found on eBay. And what was really critical is the tube manual. If you go to the Bama Boat Anchor Manual Archive, they have the tube manual for the Cencor Mighty Mite. It's a small little tester, and literally anything you'd want to test, you can do with that. As a matter of fact, I happened to mention this to someone, and they told me that they had a business, and they said they had some really expensive tube testers, but the one they used every day was the Cencor Mighty Mite.
Yeah, thanks very much for that. And the next question is, what software do you use for milling PCB? I have a CNC, but had no success milling PCBs.
Okay, well, let's see how I can do this in a way. Okay, coming up in the near future is another article in Sprat about milling PCBs. And I list several PCB milling pieces of software. And I happen to use Mach 3. Mach 3 is the software, but there's others out there. As a matter of fact, design systems, I use G-Simple, but there's a Carbide Create. So many of the machines that are out now, the CNC machines, they come complete with a GRBL software. So the milling software is actually there. If you're asking about the design software, take a look at Carbide Create, because it automatically generates several different kinds of code. It'll generate G code automatically, so that you're done with the design, you push a button, you get the code.
Okay, thank you very much. And the next one is Pete. Thank you for your presentation. What motivated you to build with tubes and valves?
Well, I've been at this for a long time, about 62 years. So I built some early on valve transmitters. As a matter of fact, it's fascinating to see we're in cycle 25 coming up. I got on the air with cycle 19, when an amazing cycle. And I actually built a QRP CW transceiver that used a 6CX8. The triode section was the oscillator, and the tetrode section was the amplifier. So my roots go way back, because we didn't have much solid state. Although I played around with solid state devices in the early 50s, CK722, the real power stuff was just not available. So that's how I got started with tubes. And then soon, when the solid state explosion, who needs tubes?
Indeed. I'm going to hand back to Brent, who's managed to get back in again. Brent. We got no audio again, Brent. Oh, we've had fun today. While Brent's sorting that out, in case we've got other people, the next question was from Bill, AB1AV. What have you suggestions for a portable battery-powered HV supply?
Actually, there is a Sprat article, and this goes back 6-8 years. A guy built a DC to DC inverter for that very purpose. And you need to search the Sprat archives, and it was really clever. I mean, he took his 12-volt battery, he got some filament transformers back to back, got some switching transistors, and that was the whole idea, was he could use a battery pack to run the high voltage supply. And of course, you only need to run the high voltage when you're transmitting. So the only thing you have to worry about is the filament voltage. But check the Sprat index. There is a supply in there that would work for this in portable operation.
Yeah, many years ago, Bill, I'm certainly one of those that we used to be able to get these very, very big batteries that we could use to power the, but not at 250 volts. I think it was, were they 90-volt batteries? Someone remind me in a second.
Yes.
From the UK. 90-volt batteries we used to use. Okay, I've got no more questions on the, oh no, I have. I'm just going to scroll down. I love playing with valves, have a drawer full of World War II octals, which I want to use. Apart from the 6V6, the 6L6 and the 807, are there any others that make good 2 or 3 valve transmitters?
Of course, you could look at a 1625. The 1625 is a 12-volt version of the 807. 6AG7s were used a lot as oscillator, as an oscillator transmitter as such, or an oscillator stage. But primarily, those are the ones you saw. Was like a 6L6, 6V6, 6F6. There may be others in there. Matter of fact, I saw a guy took a 50L6, 2 of them. And the 50L6 used to be in the All-American 5 radio receiver. And because they had a 50-volt fill-in, he series those and ran 110 volts on them. So any of the power pentode tubes would work well. You may want to look at a type 45. 45 was used as a single transmitter tube. But that predates the 6V6, 6L6. So type 45 is a good one. Matter of fact, I built a type 45 and it was like a self-excited Hartley. And you had to worry about the self-excited Hartleys because you had to keep the transmitter off the operating table, because just pounding brass would cause enough variation and vibrations that would change the frequency. So you had to worry about that. But you had a copper tubing tank circuit, and if you took a lead pencil and held the lead pencil near the tank and draw an arc about a ½ inch long.
Back to you, Brent, for the last three.
Sorry, I can't see the questions. It doesn't keep them.
So that, okay, next question. If the oscillator is running all the time, how do you stop it from blocking the receiver?
I'm sorry, I didn't hear the question fully.
If the oscillator is running all the time, how do you stop it from blocking the receiver?
That's a problem. Matter of fact, in Nick Kennedy's schematic, you'll see 250 volts is on there and it doesn't show it switched. So yeah, you'll hear the signal. The only way to do it is shut the voltage off. Well, now, a way around that is to do the grid block keying. The grid block keying would actually shut it off, is what it would do.
Okay, and next question. What's your thought on using TV pentodes for the transmitters?
Well, anything that'll work. Matter of fact, one of the circuits in there had a 6DQ6. No reason why you can't put a 6DQ5 in there, or 6DQ6, or 12DQ6. Any one of those will work. I mean, if they're used in transmitter circuitry, you can make them work as an oscillator. So why not?
And Victor Brand makes the point, a TT11 as a PA, as the PA.
I'm sorry, what was the tube number?
Victor Brand just said, use the TT11 tube as PA.
Yeah, it could be. I mean, there are a lot of tubes available. You know, the thing is, just try it. Just try it and see if it works.
Okay, Brent, that's the questions that people have posed. Do you just want to say a couple of words in finishing off and thanking Pete?
I'm back in time for the sign up. Did anybody ask about the physical size of crystals? You talked about putting the little HC49s in the 243 cases. Does the physical size of the crystal matter, and what does it do?
I think the one thing that you have to be concerned about is these plated crystals. Some of the plated crystals, when you put them in these circuits and they're drawing a little power, you're liable to blow them. So it's probably better to use the FT243s that are really designed as a primary oscillator. So that would be the only thing, is the plated crystals, you know, are used for like heterodyning operations, not necessarily running some power through them. So that'd be a concern, is the plated crystals, especially the real small ones.
Mm-hmm. Okay. All right. Well, this was great, and we're finishing on time. That's excellent. Thanks so much, Pete. Wonderful presentation. An awful lot to chew on. Hope we'll be melting some solder now and searching eBay for some parts.
Right. Well, again, visit the website, because I tried to pack a lot of information in there. You'll see the information on the power supply. There's some other transmitters in there that I built, and I show some photos on. And by the way, you can reach me at craponthebench@gmail.com. If you have any questions, I'll try to answer them for you. Be delighted to. Thank you very much for having me, and see you guys. Cheers. And again, I'm here with my best bib and Tucker.
Cheers. Thanks so much, Pete.
Cheers, Pete.